So I'm out here in the industrial quarters of Copenhagen to meet up with a group called CopenHagen Suborbitals, which is right in here. Hello ladies and gentlemen, and welcome. Today we're going to visit a group called CopenHagen Suborbitals who are trying to send a man into space with a home-built rocket. I'm here to meet a guy called Thomas, who should be right inside, and he can tell us a lot more about it. So let's head out inside and let's go talk to him.
My name is Thomas Pedersen, and I've been a member of CS since 2009. And I work here as a flight director, we call it. So I'm overall in charge of operations when we fly our rockets, and also when we do static tests of our engines. So the overall goal of CopenHagen Suborbitals is to launch a man into space. People have of course been launched into space before, but we're a small private organization and we intend to do all of it ourselves. We have a very, very limited budget, so we're developing our own technology to facilitate that we can launch a person into space. And we're not launching a person into orbit, as many people believe. We're launching a person on a suborbital trajectory, so we're basically launching up and then safely down again. So it's a very short flight. It's some way similar to what Virgin Galactic is trying. So they're of course using a sort of a plane. We're using a more traditional rocket and a space capsule that will land in a parachute. But the overall goal is to launch a person into space. It's not cheap. So we have a budget of maybe 100,000 euro a year, maybe 120,000 euro a year. And from that we have to rent our workspace here and pay all the bills for all the materials that we buy. But the core of the organization is that everybody is volunteer, so nobody gets paid anything. We of course have to buy a lot of things, but nobody gets paid. So we do all the hardware machining ourselves, or we get help from nice people around mainly Denmark. And that's the way we sort of can drive the project. So we have a group that supports us. It's called CopenHagen Suborbitals Support. It's our support organization, and they collect money basically from private investors, private people who thinks that it's a fun project. And then they donate maybe 10, 20 euros each to the group, and that way we get our funding. So what we have been doing the last couple of years is that we have developed some smaller engines. We call them BPM-5 engines. They're 5 kilonewtons, and we have flown 2 rockets on those. So we have used that as technology demonstrators, where we have sort of perfected all the systems. So to launch a rocket, you need a lot of systems. You need some ground support systems. You need other support systems for the launch. You need to be able to communicate with the rocket. You of course need to develop and build the rocket itself with all its systems and components, and you need to develop the engine. So we have developed everything as in sort of smaller scale as technology demonstrators. So now we can fly a rocket, we can communicate with it, we can land it in parachute in a smaller scale, and we can go and see the next one rocket that we have lying here. Yeah. And so that's one of the technology demonstrators. So now we're ready to scale up. And currently we're designing the next engine. So the BPM 100 engine will be a 100 kilonewton engine, so it's 20 times the thrust of our previous engine, and that will be big enough to lift our Spica rocket, which at liftoff will weigh 3.5 to 4 tons.
And Spica is the manned rocket?
Spica is the manned rocket, yes. And so it's a rocket that's about 12 meters tall, and the top 4 meters roughly is the capsule and nose cone. So the bottom 8 meters is the rocket itself with its propellant tanks.
Engine and fuel.
The propellant tanks and the engine of course, and there's also a recovery system for the rocket itself. So this is the Nexus 1 rocket, and as you can see it has flown, it has some damage to it. I would have loved to show you the Nexus 2 rocket, which also flew, and it's in much better condition because it landed better. But we currently lent that out to a museum, the Danish Technical Museum. So, but we can have a look at the Nexus 1. It has basically the same components as the Nexus 2 rocket. So, first of all, it has the engine sitting down here, and we have it's not the flight engine, so this is sort of a showcase engine. So this is the combustion chamber. You can see the double wall construction here, and then on top we have the injector, and we have the LOX dome where the LOX will enter and then exit out into the engine. So that will the engine will sit here in the engine compartment. And then for steering the rocket, we have a thrust vectoring system. And so on these rockets, we opted for a sort of an easy to implement thrust vectoring system. So what we have down here is jet vanes. So they're small graphite vanes that sit inside the exhaust of the engine. And simply by turning these vanes a little bit, then you can divert part of the exhaust in one direction, and that way you can make a torque on the rocket, and that way you can keep it flying straight up. So the guidance system on this rocket was supposed to just keep it vertical, so it wasn't supposed to fly anywhere, but just vertical, straight up. And that succeeded very well. It's this was the second flight of this kind of system. Nexus 2 was the third flight of this kind of system, and all 3 flights have basically been flying straight within 1 degree from vertical. Oh, so we're very happy with the guidance system we have developed for this. And so in the rocket here, if we move a little bit up, then we have the onboard flight computer. So this is what it basically controls everything the rocket does with respect to pressurizing the tanks and feeding propellants into the engine, opening valves. It also does all the data logging of the rocket. So when we fly the rockets, then we have constant telemetry from the rocket. So we receive, I believe at about 10 Hertz, we receive all the parameters from the rocket. So that is the most important, the pressure in the propellant tanks and the pressure in the engine. So we know if the engine is burning nominally. And we also get the guidance data such as velocity and altitude and acceleration. So we get that at all times. And so it's the onboard computer that handles all of these things. And then if we move a little bit up, then we have the liquid oxygen tank here, and in the top we have the fuel tank, so the ethanol tank. And so you can see this rocket, it landed pretty hard. So on this flight, on the Nexus 1 flight, the parachute didn't open. So it flew up and then it came straight down again, straight as an arrow, nose cone first, and it landed with about 500 kilometers an hour into the ocean.
That must have been an amazing sound.
It was an amazing sound, yeah. It was just like you see in the movies, basically. Yeah. There's actually a couple of sections missing up here. There's a battery compartment up here, and then there's the parachute section that broke off. And then so we have the nose cone here. So you can see the nose cone. It's carbon fiber. So you can see it took quite some damage, but I mean, it landed nose first at 500 kilometers an hour. So it's, I mean, considering it's
still a nose cone.
Yes, it is, exactly. So considering that it landed at 500 kilometers an hour, it's in decent condition. So this was the first of the Nexus rockets. Nexus 2 fared a lot better. It actually flew as it was supposed to, and it came up to 8.5 kilometers altitude, and on the way down it unfolded its parachute and landed beautifully in the water, and we fished it out within 5 minutes after it landed, I think. So that was a very beautiful mission, the Nexus 2 mission. So now it's a matter of scaling it up to a rocket that is 0.9, almost a meter in diameter and almost 12 meters tall.
That's a big
so
one.
It's a lot of upscaling.
Yeah.
The Nexus rockets, they weighed close to 200 kilos at liftoff, and so the Spica rocket, the big rocket that will carry a man or a woman, will weigh 3.5 tons. So it's a massive scale up, but we're very excited about it and really looking forward to start building components for it.
So I know you don't have a launch day yet, but do you know who's going to be flying it?
So initially we'll fly Randy, our crash test dummy, and then eventually, once we have demonstrated it to fly safe a couple of times, then we have a couple of astronaut candidates. So we have Anna and Mads currently that are both candidates to fly on the rocket.
Okay.
So this is a version of our BPM-5 engine. So you can see this one is not flying anywhere. It's been opened up for demonstration purposes. So you can see it's a double wall structure. So there is the outer jacket, and then there's the inner chamber wall. and in between you have a gap. So that is where the fuel will flow. So the fuel will actually enter the engine in a tube over here. Then it will stream up on the inside of the engine and to cool the engine. So the engine will of course generate a lot of heat, and you have to get rid of that, otherwise the metal will melt. So we're running the fuel up on the outside, and then it actually comes into this flange, and then it comes radially sideways into the injector part of the engine. So this is the injector itself. So the fuel will flow radially in through these holes, and then it will come out in a fan down here and be injected into the chamber. So that's the fuel component. Then we have the liquid oxygen. This will be assembled roughly like this. Liquid oxygen comes in here, and it flows out of these holes into the LOX cavity, and then it's injected through all of these holes, through the injector, onto the into the combustion side of the injector. So it's actually quite simple how this engine works. So that is what we do. We sort of simplify this sort of technology, and you can see the engine itself consists of very few components.
And what about ignition? How do you turn it on? I mean, there's no spark plug or anything.
No. So we use the good old Russian way of igniting an engine, and that is to basically stick up a pyrotechnic device up through the nozzle, and then there will be this pyrotechnic device up here. It's basically like a small fireworks piece that will ignite in here with an electric signal, and then the fuel will start flowing and it will be ignited.
Cool.
So it's basically it's a type of fireworks that used for stage shows, concerts and stuff like that.
Yeah. Cool. Oh well, if it works.
Yeah. So it's a very low technology solution. The Russians still use it on their big rockets today.
And that's the method you will use on Spica as well?
Yes.
Okay, cool.
So when we were developing our 5 kilonewton engine, then we also built this test stand to test the engine. So the test stand is consists of a couple of tanks. So we got a liquid oxygen tank here, and then we have a fuel tank over on the other side. And so these tanks, they can withstand 60 bars or something like that, pretty high pressure. The engine itself operates at 15 bars, so these can take a lot more pressure than the engine is really designed for. And so then there's a lot of piping down here. We have some main valves down here, which are the main on-off valves to let the propellant into the engine. Then we have down here some flow meters, so we can monitor the flow as a function of time. And so when we test the engine, we of course measure the propellant flow, and we measure the thrust. So there's a load cell that measures thrust on the engine. And basically from those readings, then we can determine the efficiency of the engine, so how much thrust we get per amount of fuel. Mm-hmm. And so that's really the sort of really important number to know when you're testing your engine. And so the goal is of course also to get it to operate at the correct OF ratio, so the oxidizer to fuel ratio. This one is designed to operate at an OF ratio of 1.3. So this is not the highest performing OF ratio, but so the higher you go in OF ratio, the hotter the combustion gases gets, and the more problem you have to cool your engine.
The OF ratio is oxygen to fuel ratio?
Yeah, so that's the oxidizer to fuel ratio.
Yeah.
And so if you increase that, then you also increase performance a little bit, but you also increase the combustion temperature, and that means your engine will run hotter. Mm-hmm. So at CopenHagen Suborbitals, we often take a penalty on performance, and what we gain is ease of manufacture. So we don't have fancy materials to build engines from. Our engines are built from mild steel or aluminium or stainless steel. And so that's very common building materials. It's not space grade in any way. And so to make engines out of that common materials, we take a penalty on performance. So we drop the performance a little bit, but then we, for instance, here we lower the combustion temperature to make the engine survive anyway.
Yeah.
Yeah.
So the whole rig here, that's basically everything you would normally put in a rocket. You're just taking that out and putting it on a rig to make it easier to access doing a test.
Yes, exactly. So this test stand is very serviceable and easy to get around and operate. And but everything you see here is basically also contained in our Nexu rockets, mm-hmm. In a much smaller package.
And when you then do actual launches, you go.
So when we launch rockets, we launch them from sea, which is also unusual. But so there's basically no place in Denmark on land where there's far enough to housings that we can launch rockets in Denmark, at least to the altitude that we want to launch to. So we launch from the ocean. So we have built our own launch platform, seagoing launch platform, a catamaran ship that serves as a launch platform. And so we sail to Bornholm, the Danish island, in the Baltic Sea. And so when we launch, we sail about 30 kilometers out from Bornholm, and then we launch out in the ocean about 30 kilometers out.
And stuff like that. And I know, like, if we watch like SpaceX launches, they often have video cut out when the boosters come back down. And I believe that's because the platforms will begin to wobble and they lose satellite connection.
Yeah.
I've heard you had a rather ingenious solution, or you've done something that people said you couldn't when it comes to live streaming rocket launches.
Yeah, so we have some clever people on the that builds so they build antennas in their daytime jobs. So they've devised a system that we use. So when we're out at sea, these 30 kilometers from land, then on our ship, our mission control ship, there's an antenna that is controlled in azimuth. So it points to a point on land, and there's a satellite dish on land. So we send a Wi-Fi signal 30 kilometers and receive it on a satellite dish on land, and then we stream it to our workshop here, actually.
Like a gimbaled antenna that's then beaming Wi-Fi 30 kilometers over water onto land and then streaming it from there.
Yeah, exactly. So it's a 30-kilometer Wi-Fi link that we developed ourselves, which is so I don't know that much about electronics, but what I hear it's quite cool and quite unique. And I know that so we use some Ubiquiti stuff for it, and we were contacted by them, and they said it wasn't possible to do, but we're doing it anyway somehow. But our electronics people have
your live streams beg to differ, I guess.
Yeah, exactly. So we strive to stream as much of it as we can, because we will live from the support of people. So our YouTube channel is one of the places where we gather a lot of support, and our blog and our website. So the streaming part is a very essential part of keeping us going.
Yeah, cool. Finally, I just want to say a huge thank you to Thomas and everybody else I've been talking to at CopenHagen Suborbitals for helping me out with this project. I've linked to their channel over there. We can go and see if you want to see more about them and see what they're doing, and also have a quick video from their channel below.